Should be live in just a moment. Okay. I believe that we should now be live on YouTube. But drop us a note in the chat if you can see us. Good morning on this beautiful Tuesday. I'm Sophie, and Jamie is joining me today to help answer some questions and keep me on track. So let us know if you are there in the chat. If you have any questions throughout the stream, please just drop those questions in the chat. Jamie will stop me, or he'll try to answer them if he can directly. But yeah, we always love to know where people are joining from. I see someone from Greece and from Alabama. Very exciting. So let us know. Cool. Alex Flaxen says, you're live. Thank you. Awesome. So I guess we'll get started, and we'll kind of jump right in. It's good to know that YouTube is working. We're back to last week. We did a stream in the office. This week we're back from home. So we were really high tech last week, a little lower tech this week, but hopefully we'll get the office setup up and running more frequently in the future. So I'm going to go ahead and share my screen, and then we will kind of jump right in. Share. All right. Can you see that, Jamie?
Yep.
Okay.
Yep.
Cool. So this was a little bit late onto the GitHub page. So if you haven't had a chance to take a look through these notes, that's totally fine. I'm actually going to, before we even get started with these notes, I just want to show you on Codecademy where you can find the article that covers the topic that we're going over today. So if you search linear regression, you'll see this linear regression in Python course. This is the course that we're going through in this series. And right now, we've kind of talked about simple linear regression, multiple linear regression. Last week, we talked about interactions and polynomial terms. And then this week, there's this article in here on log transformations and more. This stream is going to cover even more of the and more part of that. But if you take a look at this article, there's a bunch of helpful information here, and it explains all of this with an actual data set. Today, I'm going to use some simulated data, and I'm actually going to kind of take you behind the scenes, if you will, and show you how I'm simulating data, because I actually think that this is a really useful skill as a data scientist, as a statistician, to be able to create data that follows some, or that represents some situation that might occur in real life, and then see what happens when you try to fit a model on that data. So it's really useful for debugging as well. So here, I'm just in this code uploading or uploading a bunch of, or loading a bunch of libraries. I see someone said, Sophie, you did not finish the modules. I did finish the modules. I actually have reviewed all of them very, very carefully. But yeah, it doesn't, when I go through on Codecademy, it doesn't mark them as complete. I actually wrote some of the ones that it says I haven't completed, which is funny. Okay, so anyway, so we're gonna simulate some data. So what's happening here, the reason I have these random seed functions in the code is just so that if you're downloading this code on your own, you get the exact same numbers. This will all work without this random seed. It'll just generate slightly different data every time. Now, what I'm doing here is I'm just using, within the NumPy package or NumPy library, there's this random module that has a bunch of basically probability distributions that you can sample from. So if I sample from a normal distribution, I'm basically just like sampling from a bell curve, and I can specify the mean and the standard deviation of that bell curve, which I've specified as 167 and 3. And then 3 is the variance or the standard deviation. And then 150 is how many values I'm sampling. So I'm just going to break this down for a minute so that you can see what I'm doing. But if I run this and just print out the results, I'm just getting a whole bunch of randomly generated numbers that have a mean of 167 and a standard deviation of 3. So you can see all of these numbers are pretty similar to 167. They vary around that, usually within 2 standard deviations or 3 standard deviations. So like you're not going to see many numbers that are more than 9 greater than 167. So you're not going to see much that's larger than 176. Or smaller than 167 minus 9. But basically just randomly generating some numbers. And then in this next step, what I'm doing is I'm taking the numbers that I just randomly generated, and I'm just like multiplying them by some number and adding some number. So you might recognize this as basically the equation of a line. I actually grabbed these numbers from a regression. And then I'm adding some random noise. So if I didn't add this in, and you can see a plot down here of the data that I just randomly generated. This is the height and this is weight, right? That I randomly made up. If I didn't add this random noise, these would all be in a straight line because we would be simulating our weight variable to be exactly linear with height. So I can actually demonstrate that really fast. If I do something like this, I get a bunch of points in a straight line. And then now, right, I add this back in. I've simulated some data. It looks like this. I'm calling it height and weight just to make this, I don't know, I guess a little bit more grounded in like a physical example, but yeah, that's all we're doing here. I see, I see a question about, are we doing the OLS without an API? So I assume you're asking about this like, this statsmodels.api library. If you're not asking about that, then you can clarify. But so we actually managed to do it without the library at all in the week that Nitya was joining me. I think that was 2 weeks ago. We did it with some matrix algebra in NumPy. And then there's definitely some code throughout to do this in Sklearn as well, if you're interested in learning another library. But today we're going to still stick with this statsmodels.api module because, again, it gives us some good information that's useful for debugging models. Cool. All right. So today we're going to talk about some of the things that can go wrong when you fit a model. And then we're going to talk about some of the ways of fixing those things. Sometimes you're going to notice that something went wrong because you get a warning when you fit the model. Sometimes you won't get a warning and you'll need to check the assumptions of the model, and then you'll see something that surprises you, and that will clue you in that you need to do a little bit more investigation. So I'm going to start by just fitting a model with this data that I randomly simulated. And we've seen something like this before. I'm going to fit a model where I predict weight based off of height. And then when I fit this model, I see, and we've seen this same warning before, but I see this warning that says the condition number is large. This might indicate that there are strong multicollinearity or other numerical problems. Okay, so I think last time we saw this, the strong multicollinearity part, we talked about a little bit more in depth, and we discussed how that has to do with having predictors in the model that are collinear with each other or correlated with each other. And we talked about why that might not be a good idea to include multiple predictors that are highly correlated. But in this example, we've only fit this model with one predictor. So there's no chance that we have correlated predictors. So we need to think about what else could be wrong in this situation, what else could be causing this warning. And so one of the things, let's look at this picture, that you might notice when we first look at this, this graph is that it's automatically in Matplotlib is plotting this so that it perfectly fits within the axes, but we see that it starts at like 160-ish or a little below 160 on the x-axis, and it starts at like 54 on the y-axis. And so if we get this intercept of -23, and we talked about this, I think, in one of the first live streams, in order to visualize what that intercept looks like, we really have to zoom out a bunch on this plot. So I think I have, yeah. So here this plot is again. I'll pull this up here so you can see it all in one place. Right, so if we just plot this, looks like this. If we plot it and we change the axis so that the x-axis starts at 0 and goes up to 180, because that's roughly how far up it goes on this x-axis. And then on the y-axis, we have it start at 0 and go all the way up to 70. We're going to get this kind of like squished plot, which is to say that like the -21, and here I can even have the y-axis go down to like negative, or was it -23? Yeah. So we'll have it go to -25. This is coming from the fact that if I drew this line in, and we can even, let's draw it in. We can do equals dot array 0, 180, and then y. I'm doing it the old-fashioned way. We'll even grab these. So the intercept is -23, and then the slope was 0.5166. If we add these to our plot in the form of a line, right, we see that, so this is our regression line, and the -23 is the y-intercept. And the reason it's -23 is that in order to draw this line, we've got to go all the way back to the y-axis, which happens at x equals 0 or height equals 0, and then it hits at -23. Jamie, do you have any thoughts about like why this might be problematic, or like what might happen if the data were to just change slightly? Like if we changed the slope of that line just like ever so slightly, because we had a point down here all of a sudden. What might the issue be?
I think like a main issue would be that like a slight change in the slope. So like any outlier that like could potentially change the slope a lot would change the intercept like pretty heavily. Um, so I think like that is one issue I see. Is that like the main
Yeah.
issue you're talking about, or?
Yeah, that is exactly what I was intending. So, right. So this is like a kind of unstable estimate for the intercept because, and I think we talked about this a little bit when we first talked about the definition of an intercept or like the interpretation of an intercept. So, Jamie, I don't know. I don't remember if you joined this first live stream or if you're caught up on this, which it's totally fine if not. But do you remember how we would interpret this intercept, this like value of -23? Or
Yeah. Yeah. So since we were talking about, I think it's x-axis is height, y-axis is weight, or is it? Yeah. So this intercept is basically saying that a person who has a height of 0, I guess centimeters, would be expected to have a weight of negative, I think it's like 25, 22 or something, pounds or whatever, or kilograms or whatever the scale is. So it's probably like not super informative here, or like not super what's it called? Like sometimes you'll have intercepts that like do make sense. Like if you're doing like hours studied versus expected test score, like 0 hours studying and expected test score, like that could make sense. I don't know anyone who has a height of 0 centimeters who has a negative weight. But so yeah, I think this one is potentially a little bit less informative. Yeah.
yeah, exactly. I realize it maybe is more useful if I use this like SNS scatter plot, and because then I think it like plots the or at least gives you the labels. We'll do that. Let's see if that works better. Yeah, there we go.
Thanks.
So exactly. So this is the predicted value of weight when height equals 0. But just like Jamie said, there's no such thing as having a height of 0, right? We have no data all in this part of the plot. So drawing the line there, like we can say that there's this relationship, but really we only want that relationship to want to say we really only care about that relationship where the data exists, which is only in this part of the plot. And so we're estimating something that's not really of interest to us, and it's also an estimate of something that's really easily changed by just like small changes in the data because it's so far out from where the data is that it's kind of unstable. So there's a number of things that we can do to fix that. And so this is maybe one thing that's not in the article that I originally wanted to include in this course, and we just didn't have time. But I'm going to demonstrate it now. So actually, before we even get there, one thing I also sorry, I'm changing my mind as we go. Let's fix this first, and then we'll go back and talk about some of the other assumptions. So there's a couple different ways to fix this. One way to fix it is simply to center the height variable. And so I'm gonna talk you through what centering means in just a second, and we can actually do it together. So to center something, center a variable, all we do is we take the mean of that variable and we subtract it from every single value. So I'm gonna go ahead and in my data, I'm going to find the mean height. So I'll print that out first. So the mean height in this data is about 167 centimeters. And then what I'm going to do is I'm going to subtract that from every value in the height column. And what this does is it just creates a whole list of values of heights with the mean subtracted. So Jamie, do you want to like talk through what are these numbers now interpreted as? Like if we see 4.928, what does that mean?
So I think that means that like this specific like data for the specific data point, it's like 4.9. Like the height, like this person's height is like 4.9, I think centimeters greater than the mean. So it's basically like the distance just like from the mean.
Exactly. So yeah, so this person is 4.93 centimeters above the mean in terms of their height. This person in the third row is very, very close to the average height in the data set. So if they had a value of 0, it would mean that they were average height. So what we can actually do is we can create a new variable, we'll call it height centered, that contains these values. And then I'll print the first few rows of the data again to just take a look. And so all we did was we said, okay, we've got weight, we've got height. Now I want to create another column that's called height centered. And these values are now centered at 0, right? So a value of 0 means average height. Anything above that means they're above the average height. Anything below that means they are below the average height. Did I do that right? Yeah. Yes. Okay. So now what we can do is we can refit this model, but use centered height instead. Height centered. And you'll notice that that other warning went away. So remember the first time we got this, the condition number is large. This time that went away and we just get standard errors assume that the covariance matrix of the errors is correctly specified, which I believe we get no matter what. That's always an error or a warning here. Okay, so that's one way. And we're just kind of dipping our toes in that we can start to transform our data. And by transform, I mean take existing data and kind of do something to it so that we can fit a model that is a little bit more stable, that doesn't create warnings, that is potentially like a better fit to our data, is easier to interpret, all of the above. So I think one thing that is maybe useful before we move on to more complex example is to now look at what this picture looks like. So let's go ahead and I'm actually going to use, I like this lmplot function sometimes because it just saves us a little bit of time. So let's replot on the x-axis now height centered, and on the y-axis let's replot weight, and then the data is just called data, and this will automatically plot the regression line. Show, run. Cool. So now we see that the weight variable looks exactly the same, but height centered, right? Like the middle of these data points is around height centered equals 0, which makes sense because that's the mean. And let's actually let's add like a vertical line to this. Okay, I have the code to do that somewhere. It's basically like this, but AX line. So this right here, where I've drawn this dotted line, this is the y-axis now. So, so now the place where we cross the y-axis, and I think we can estimate, I'll fit the model in just a second so we can see what it is, but it looks like it's around like 62 point something, maybe 63. That value, Jamie, do you want to take another stab at interpreting that number?
So I think it's like if you have a mean, if you have like a height that is equal to like the mean of the data, then you're, well, so I guess it's like when we centered it, we're like at 0 now. So like that is the y, that's like the x equals 0 point. But I'm guessing we would say like, if you're at like a height of whatever like that pre-transformation was, then that's like what you would interpret it.
So,
Like,
okay,
it's like
so
if you have like height of 62 or something or whatever the mean was, then you have like an expected weight of x of like 62 point something.
Yeah. Exactly. So if your height centered value is 0, it means that you are average height.
Yeah.
So the expected or the average weight of someone who is average height is 62 point whatever, is how you would interpret that. So now we've got a more interpretable value. And it's a little more stable, right? Because like the intercept is now kind of in the middle of all of the data. And so if we have another point somewhere, it's going to be less likely to change what this value is than before. So, cool. Actually, I think let's really quickly fit the model and just see what this looks like. So if we go ahead and fit our model, but now we use height centered, we get an intercept of 62.7. Our slope on height centered 0.5166 is exactly the same as our slope on height. So the slope of our line didn't change. It just changed the intercept. And now that 62.7 is average weight of someone who's average height in the data. And so we've got a situation where we can interpret it. It's more stable. We don't get errors. Oh, I already did this down here. Sorry. Okay, cool. If there are any questions in the chat, please let me know. Otherwise, I'm gonna now move on to some log transform stuff. So I think one of the things that's really challenging about data transformations in general is that there are a ton of different ways that you can transform your data. And it's hard to know exactly which one to do in any given situation. So one thing I want to say is like, there are no hard and fast rules, and there's also way more options than what we're going to cover today. For example, we could, instead of centering, we could just standardize everything. So we could also divide by the standard deviation. That would change the slope and change our interpretation of the slope. But there are definitely situations where we'd want to fully standardize instead of just centering. I also see a question, can you explain the shaded area on the graph around the best fit line? That is a great question. So this LM plot function, it automatically creates this like confidence interval around the line, which basically shows how confident we are that the line is where it's pictured. So, or like how sure we are that the line is here. So you'll notice that like on the ends of it, this shaded area is wider. Here, I can zoom in. Whoop, where'd it go? Right, the shaded area is wider on the ends because in this, like in this part of the graph, where there's not a lot of data. And so we don't know like if we had one more point, we don't know if it would be like close to this, if it would be here, if it would be up here. And that could potentially shift this part of the line a lot more than in here where the bulk of our data is. We're more confident that the line goes through this point. Actually, I think it would be potentially interesting. Can we do like a LM plot on this? What happens if I do that? Interesting. So it won't even graph it outside of where the data is, I'm assuming. Let's make this like 130 or something. Yeah, you can see it's like graphing this line in here. It won't even graph it down here, but you could imagine, and it would be really nice if it did, because I think you could visualize that if you see how, and I know you have to look kind of closely, but if you see how like the confidence interval is really tight in here, and it gets wider and wider and wider, it would just get wider and wider and wider the further away from the data you went. So you could really see what I was talking about before, where if you drew this line all the way down here, that confidence interval would get really wide around here, meaning you're like very uncertain about what that intercept is that you're trying to estimate. Oh, okay. I see Alex noted that SNS.lm plot is SNS.regplot in the latest version of Seaborn, FYI. Yes. The reason we have been using LMplot, I think LMplot still hasn't been deprecated as far as I know. And we had an older version of Seaborn on Codecademy. So we don't have regplot, I think, yet. But that is good to know. Thank you. Oh, and then I see another comment. Licky DD says, I think they are still two different options with slight difference, figure level or not. Not exactly the same arguments. That is interesting. I actually did not know that. I'm gonna just look it up really fast. I think this is kind of cool. Interesting. It looks similar, but it looks like it has some additional options. Let's see. Yeah, LMplot still definitely has not been deprecated.
I think we used regplot for one of the off-platform, like the off-platform data analyst final portfolio project. Remember?
Should we just try it? See what happens?
No.
Oh, no.
Oh.
Z, X, Y, and data, right? Oh, it's because I haven't recreated this yet.
Mm.
So I guess in this example, it basically looks the same.
Yeah.
But interesting. It would definitely be interesting to do a more careful comparison and see what the real differences are. Okay. So before we kind of move into the second half of this live stream, I think it's useful to take this data, which besides the fact that we had this issue from before where like the intercept was kind of far away from the data points. Besides that issue, this data is simulated such that it fits a linear model really nicely. In fact, I think it's kind of cool to just see, just prove to yourself that like things are working as they're supposed to. So when I simulated this data, I used some numbers from a regression, but I simulated it to have an intercept of around 21.7 and a slope of about 0.5. And then but I randomly generated the point, so it wasn't going to be exactly these numbers, but this is what I kind of simulated. I simulated an exactly linear relationship with some error. And then when I fit this model the first time, my intercept was close to the -21, and the slope was close to the 0.5 that I originally kind of set out to use to create the data. So with that said, right, like if I create data that perfectly fits a linear model, then I can see kind of what my checks of the assumptions of linear regression should look like if everything is kind of perfectly perfect for the purposes of linear regression. So I'm going to take a look at two different assumptions of linear regression. So the first assumption that we'll talk about is homoscedasticity, which is a very fancy word, but it's pretty, I think, hopefully easier to understand once you take a closer look. So homoscedasticity essentially means that there is equal variation of the outcome variable for all values of the predictor. So, or predictors, if you're in multiple linear regression world. So here, for height-centered or height, either one, we notice that like the amount of variation on this part of the line is pretty similar to the amount of variation over here. And so because the variation is roughly the same for all values of height, the variation around the line is roughly the same for all values of height. This data follows the homoscedasticity assumption of linear regression. And we actually, again, we created the data to do this because we added random noise centered at 0 with the same level of variation for all of our values when we first created the data. And so the way that we often check homoscedasticity is we get the fitted values for our model. The way we get the fitted values is we just predict, we get basically like the predicted values for the original data itself. And so I will kind of show this. I think we skipped over this in the first week, but I think it's like important to kind of come back to now. So the fitted values here are just the predicted weights for everyone in the data set. Then we can calculate the residuals, which are the difference between the actual weights of every person and their fitted value or their predicted weight. And then we can plot the fitted values against the residuals. And we expect that, the residuals against the fitted values. So these are the residuals, right? The y-axis is the residuals. These are the fitted values. And we expect that the residuals should be centered at 0, right? Because on average, all of the points should be like equally, or basically like some of the points are going to be below the line, some of the points are going to be above the line, but the line was defined such that it's kind of going through the middle of all the points. It's minimizing that vertical distance between all of the points in the line. And so we expect there to be just as many points below the line as above the line. And we want this, basically we want this plot to just look like a splatter. We don't want to see any patterning. We don't want to see that like the variation on this side is different from the variation on this side. And I'll show you what that would look like in just a second. We also generally want to take a look at the distribution of the residuals. And we expect that distribution to be roughly normally distributed. So we don't want to have a lot of skew. We don't want to have like a bunch of really small residuals and then very few large residuals. So this looks pretty good. It looks pretty symmetric. There's one kind of hump around 0, and we feel pretty good about this. But now let's go into a land where this is not the case, and then take another look at how we could kind of get around that. So going way down. Okay, so here is some more simulated data that violates the homoscedasticity assumption. And so basically, I simulated this data so that the this error term is related to one of the predictors. And then that means that like essentially for larger values of age, which I'm gonna make my predictor in this made up data, I'm adding more variation, and for smaller values, I have less variation. So, okay.
Is that kind of showing up in the, I can't tell if I'm like seeing this wrong or not, but the shaded area for the plot, it's like a little bit wider for like the data that's more like varied in like the higher age numbers.
Yeah, I think it is. That looks right. Okay, so I just honestly made up again some labels so that we would have something to kind of refer to instead of just calling it variable 1 and variable 2. So let's just say this is like age of person. There's some very old people in this data, but that's fine. 120, yeah. And this is like how much they spent, maybe should we say like on healthcare per year or some, I don't know, yeah. Like making it up, totally fake data. But we see this kind of funneling basically where there's like very little variation around the line for small values of age, and for large values of age, there's a lot of variation in spending. Like people who are 100 years old are spending between 40 and 140 versus like people who are 50 years old are really just spending between like 42 and 47. So we're not going to get any warnings. Like if we fit this model predicting spending based on age, we're not going to get any warnings at all. Besides this, like our typical standard errors assume that the covariance matrix is correctly specified. But if we were to go through and take a look at that plot that we just made for the last set of data, we'd see that we get this kind of like, so again, this is the residuals against the fitted values. We start to see this like funneling effect. I think the like official term for it is funneling. I don't know, at least that's what I've seen. So this is happening, remember, because if we go back to this plot and say, and this is the line that we're fitting, the residuals are going to be really small down here. Like these are very small residuals. And the residuals are going to be really big over here. Like this point, for example, is going to have a really big residual. And this point is, and this point is. So we've got smaller residuals for smaller values of age and larger residuals for larger values of age. And that's what we're seeing here. Smaller residuals on one side of this graph, larger residuals or a bigger range of residuals on the other side. And if we look at a histogram of the residuals, they're still roughly normally distributed. So they're still, in this example, residuals that are small and residuals that are large. And it's still more common for to see small residuals than large residuals. But we're violating one of the assumptions, the homoscedasticity assumption of linear regression. So I'm going to break for a second because I see that we have like 12 minutes left, and I'm going to try to save a little time, I think, by looking at this article really fast. So in this article, we see an example where there's both the issue of homoscedasticity is violated because you see there's like a lot more variation over here than over here. But also the issue, also in this example, the residuals are not normally distributed. There's going to be, I think, a lot more large, or let's see. Yeah, a lot more, like a lot longer tail of large residuals than small residuals.
Is there a point at which for like it to like hit the residuals are normally distributed? Is there like a point at which like you realize that they're like it doesn't like hit the it's like not like a good amount of normality? Because like sometimes like you'll have a graph where there's like some slight skewness versus like a lot of skewness.
Yeah, that's a good question. So there are some more rigorous ways of checking the normality assumption. One is a QQ plot, which basically allows you to visualize how far off the points are from like what they would be expected to look like if it was a perfect normal distribution. But then there's also a hypothesis test. I'm blanking on the name of the test, but I'll look it up and I'll post it somewhere later. But there is a hypothesis test you could run for normality, which is something that people sometimes do, and just like set a significance threshold ahead of time, and then yeah.
Is it the Shapiro-Wilk test?
Yep, that's it. Yeah. I was like thinking that it started with a W, but yeah, yes, Shapiro-Wilkes is the one that I've seen most commonly used. Okay, so the other thing like that I notice about this right off the bat is that this is kind of, this data looks kind of not linear in that, like if I were to draw a line through this set of points, I would draw a curved line, right? Like it would probably start up here and it would like curve around to here. And whenever you see kind of like this non-linear relationship, that also can be a indicator that you maybe need a different method to model this relationship, whether it be adding a polynomial term or in the case of a log transform. Log transform can help manage this like homoscedasticity violation, which would be called heteroscedasticity, I believe. And then also help with this lack of normality among the residuals. I also see Alex said, I think some people also check the two parameters, skewness and kurtosis, to assess normality. Yes. Yeah. So there are summary statistics that you can calculate called skewness. And then I think kurtosis is like how it's like peakedness of the distribution, I believe. And you can calculate those values and then use that to assess if you want like a not hypothesis test method. Yeah, for sure. So basically, log transform, generally what we would do is we would take the log of the outcome variable and then fit that in the model. So I'm going to do that back in my code. Instead of having spending, I can, just like before when I had centered height, I can do log spending, and I can end up with, therefore, a new column where I've got the log of my original spending column. And then if I plot age versus log spending, again, you'll see that this looks a little bit better than the original data. It's still got a little bit of funneling, but it definitely like improved that slightly. So again, like this was the original where we've got quite a lot of funneling happening. And then this is after we plot age versus log spending instead of age versus spending.
Is there a way to like know that like you should try a log transformation on a like y variable? Like is like funneling like a good time to like try a log transformation? Or
yeah, so there's lots of reasons why you might try it. One reason, so I think like one reason that you might try it is if you see that funneling. Another reason you might try it is if you have skewed residuals. So like a lot of times what happens with the skewed residuals is that you have nonlinear you have a nonlinear relationship. So like you could imagine if these points were even further like above this, where it was like points really following like this kind of a line, that kind of shape, you end up with really small residuals down here and then really large residuals up here overall. And so you end up with this like weird distribution of residuals, which really comes from this like non-linear relationship. That's another time to try a log transform. And also like right off the bat, sometimes you'll just notice that you have a outcome variable that probably benefits from being put on a log scale. So a lot of the time that will happen with measurements like salary or cost of something, rental price, something like that, where you end up with a really skewed distribution of your outcome variable, or like very large numbers down to like very small numbers. Like in this case, we have a whole bunch of values that are close to 0 in terms of this like phones variable. And then we've got some values up to 1,000. And so taking the log just helps normalize this like y variable. Like I'm pretty sure if you were to plot the distribution of phones, it would be skewed. Cool. All right, we are running tight on time, so I'm actually gonna kind of switch over to showing you. Well, I can show you quickly on this example. So we took the log transform, we fit our model with log spending instead of regular spending, and then we end up with a lot less funneling in this plot. There's still some funneling for sure. Like it's not perfect, but this definitely helped us build a slightly better model. I think, I forget if there's a picture in this article. Yeah, so now I think this one is maybe a better example. I was trying right before this to simulate some data to kind of show you something that looks more like this, but I was being slow to simulate data. So I think it's maybe better to just show you this. But if we look at this relationship now between log phones and birth rate, we see that the relationship between the log of phones and birth rate is a lot more linear than the relationship between phones and birth rate. And so by taking the log, we've made this more linear. We've addressed the homoscedasticity issue a little bit more. There's less of this funneling in the original plot. And so when we take a look at a histogram of the residuals and the residuals against the fitted values, we end up with something that looks a lot more reasonable. This looks a lot more normally distributed, and this looks a lot more like a splatter of points. We don't get that same funneling as we had before. There's a whole bunch more in here that I was hoping to cover today, but I don't think we're gonna have time, about the interpretation, or like how you would interpret a model where you took the log of the y variable or the outcome variable. It's really just a bunch of math. So what you're fitting in this case is like log of the outcome variable is equal to this like intercept plus slope times birth rate. And so if you want to solve for just like phones, then you have to exponentiate both sides. So I think in Python, if you do np.log, it's the natural log. So, right, you end up having to exponentiate, mean like take e to the log of both sides. And so you can kind of work out what this relationship is if you exponentiate both sides and solve for this. I'll leave that to everybody to read the article on your own, but I hope that this live stream gave at least some examples and some first sense of how you might want to transform some of your data so that you can more effectively model it using linear regression. Cool. So with that, I will wrap things up. We've been having office hours on Thursdays on Discord, so you can join us there if you have any questions. I know there was a really good question when I checked yesterday, and I'm going to get to that today, try to answer that on Discord, but we'll discuss a little bit more on Thursday, and feel free to join us if you'd like to ask anything. There's also a chat on there, so you can leave us any questions. if you want us to like take some time to think about it beforehand and give you a more comprehensive answer. Cool. Anything to add, Jamie?
Yeah, no, thanks for letting me join you today, Sophie.
Yeah, thanks
As
for helping me
always, it
out.
was very fun and I learned a lot.
Good.
I'm sure everyone watching did too. So
All
thank you.
right. Well, thanks for joining me. All right. Have a good day, everyone.